Hi, this is class 14, the part 4 of multiple regression model estimation. This is the last part. This lecture is going to be a very short one. I think we're going to be able to do it in half an hour. And the reason is that, historically, the majority of this lecture is going to be done in the classroom set. And I'll give you, half an hour, 45 minutes to think about a couple of slides, and then we do it as an exercise together. So for that reason, I'm going to make this lecture video relatively short, and then we're going to leave the rest, the chunk of the exercises to do in the class together. All right, let's begin. Okay, so in the previous lecture, we talked about over-specification and under-specification. We said that if we have any kind of misspecification in the model, we need to see what will happen to the unbiasedness, look at the expected value, and the variance. So we have already seen what will happen to the variance of beta hat 1, beta hat 2, and etc. in the case of over-specification and under-specification. But in this couple of slides, basically slide number 2 and 3, I will give you an exercise, and I really want you to think about this exercise before when you want to come to the class in our next class. So please take this exercise very seriously, because if you do it properly, it's going to put together everything we've learned and discussed in chapter 3 so far. Okay, so we will be talking about the variances in misspecified models, right? And the idea is that there's a trade-off. We talked about this trade-off, the trade-off between bias and variance. The choice of whether to include a particular variable in a regression model can be analyzed by going over the trade-off between bias versus variance. And as I said earlier, you cannot have it in both ways. So usually when you want to have a smaller variance, you end up having a larger bias. And if you want to get a smaller bias, you end up getting a larger variance. So there's always this trade-off between the two. Okay, now let me set the scene for you. Again, take it as an exercise, and we're going to do it together in the class. But here's the idea. Imagine there is this true population model, and by the way, which is unobserved out there, right? There are 3 variables out there, y, x1, and x2. They are related with each other. Again, in the population, we believe that there is this true model out there, rather like this. Okay. We are going to estimate this true model, unobserved true model, using 2 models. Model number 1, which include both the x1 and x2 in the model. And we're going to use hat for the predicted version. So we're going to reserve hat for model number 1 and tilde for model number 2. In model number 2, we're going to drop x2. Okay, so it only includes x1. Okay. Now, here's the exercise. I want you to look at this slide and make sure that you can answer basically all this. You can double check all these statements. Okay, so what are these statements? Basically, on the left, we have our, what we call it here, model number 2, right? So here is our model number 2, and we show everything with tilde, right? And there's only one x1 in the model. So this is your y, this is the x1. And x2 is dropped, but where is this x2 depends on different scenarios, different cases. So sometimes x2 is here, sometimes x2 is here, sometimes x2 is here. Okay, so I want you to think about these 3 different cases and confirm the statement here. So for instance, and so again, on the left, this is our model number 2 when we have x1 in the model. On the right, it's our model number 1 when we have both x1 and x2. And again, we're using it with hat. Okay, we're showing it with hat. And for your reference, I wrote down the, sorry. Okay, for your reference, I put down the equation for the variances below each model as well. So let's see. So here is the equation for variance of beta tilde 1, and here is the equation for variance of beta hat 1. And so these are, again, x2 can be here, or here. On the right hand side of model number 1, we have y, x1, x2. Again, x2 can be here, or here, or here. I want you to think about different scenarios for x2, and then compare the unbiasedness and the variance of the beta hat versus beta tilde in each scenario. And I already give you the answer, so here are the answers. So for instance, if here, if x1 and x2 are uncorrelated, then beta tilde 1, beta hat 1 are both unbiased, but the variance of beta tilde 1 is greater than or equal to variance of beta hat 1. So I want you to think about when is the case that it's greater, when is the case that it's equal. Okay. When x1 and x2 are correlated, then we can have two cases. x2 is irrelevant, beta 2 is equal to 0. The correlation between x2 and y is 0. And x2 is relevant. The correlation is not equal to 0. Then in either case, so look at the first one. When x2 is irrelevant, then beta tilde 1 and beta hat 1 are both unbiased. The variance of beta tilde 1 is going to be smaller than the variance of beta hat 1. However, if x2 was relevant, then the beta tilde 1 is biased, beta hat 1 is unbiased, and the variance of beta tilde 1 is again less than the variance of beta hat 1. Okay, so I want you to practice this exercise at least a couple of times and make sure that you can confirm all the statements. And then we will be able to talk about these three bullet points. So there's a trade-off between bias and variance, and the variance will shrink as the sample size gets larger. So this is basically telling you that, you know, having a large variance is not necessarily very bad news. You know, if you can, I don't know, work with some other samples that the sample size is larger, then multicollinearity is going to become less and less important as this sample size gets large. However, the bias will not go anywhere, so the bias will not vanish, even if the sample size increases. Okay. All right, so I leave it as an exercise, and now let's continue our discussion. The rest of these slides are pretty much straightforward because we have seen them before in simple regression model. We are going to estimate the error variance in multiple regression model. Now, as you remember, in simple regression model, we said we have a sigma hat square. This was the unbiased version of the sigma square, and we had a theorem, and we simply needed to divide the variance of u hat by the degree of freedom. Everything is the same here in multiple regression model. In multiple regression model, whatever the summation of the residuals are, you have to divide it by degree of freedom, and we know that the degree of freedom in multiple regression analysis is n minus k minus 1, or we can write it as n minus k plus 1. K plus 1 is the number of parameters that you're estimating, number of estimated parameters. So parameters, okay. And there's this theorem. Again, we have seen this before in chapter 2, so let's quickly revisit that one in chapter 3. The only difference is the denominator. Denominator used to be n minus 2, now it's n minus k minus 1. Okay. And basically, it's called the unbiasedness of the sigma hat square. It says that if you have assumption number 1 through assumption number 5, so now we have to add assumption number 5, the homoscedasticity 1 as well. With those 5 assumptions, we can say that the sigma hat square that we're calculating here is an unbiased estimator of the sigma square. How do I say it in mathematical formula? If I want to say that one variable is unbiased version of the parameter, so I say the expected value of that whatever variable here is sigma hat square is equal to sigma square. So if this is the case, then we say sigma hat square is an unbiased estimate for the sigma square. Okay. All right. And as we discussed it in chapter 2, you know, there are formulas that you can use to derive the standard errors of the beta hat 1, beta hat 2, and in general beta hat j. But again, we never need to be worried about the calculations. In R, automatically all these numbers are going to be driven for us. So, but in terms of notation and terminology, I want you to be aware that whenever we are using sigma square in the model, because this is something unobservable and it's a property in the population, we call it the standard deviation, SD. Okay, so the true, and basically we say the true sampling variation of the estimated beta j is going to be shown by SD, standard deviation of beta hat j, and this is the formula. Okay. Basically, whatever the formula you use to have for variance of beta hat j, just put it under the square root, right? Now, if I replace this sigma square by its estimated version, sigma hat square, because we are estimating that number, we are using an estimated number already, instead of standard deviation, we call it standard error. It's no big deal, to be honest, if you call it standard deviation, but if you want to be accurate in terms of terminology, This is called standard error. I'm not going to test you on that, what is standard deviation, what is standard error, because honestly, even myself use them interchangeably, and lots of my colleagues do the same. But just be aware that there's a slight difference between standard deviation and standard error. So standard error is the one that you're already using some estimated numbers in it. Okay, and OLS is going to be able to calculate these numbers for us. Here is how the R is going to give us back all those numbers. Again, by now you're quite familiar with these tables. You know how to read them, but let me quickly look at the Stargazer output. In chapter 4, so this is chapter 3. In chapter 3, we haven't talked about the t-stats, p-value, and etc. So maybe it's always better to use the Stargazer output. But in chapter 4, when we do hypothesis testing and things like this, then we need to, you'll realize that using this summary output is going to be more beneficial. Okay, but here let's go back to our Stargazer output. And so what do I know? This is my, for instance, beta head 1, standard error of beta head 1, beta head 2, standard error of beta head 2, beta head 0, standard error of beta head 0, number of observation 526, R squared 22.5%, adjusted R squared, we're going to talk about it in chapter 4. And then the degree of freedom, it's n minus k minus 1. So n is 526 minus k minus 1. What are the number of coefficients, slope coefficients? It's 2 minus 1, which is the intercept, so it's 523. So that's the degree of freedom. Okay. All right, now let's talk about the efficiency of the OLS estimator. Okay. Basically, we want to say that, let's say there are many different estimation techniques out there. In general, we call them estimator. So OLS that we have talked so far is only one estimator. There are different other estimators out there that are going to take the x and y and give you back the beta hat 1, beta hat 2, beta hat 0, and etc. So OLS was only one engine. So let me remind you that. What was OLS doing? OLS said that it was a rule, right? It was a technique. It was an optimization technique. Give me the data, x1, x2, and etc. I will give you back beta hat 0, beta hat 1, beta hat 2, and etc. So this is what the OLS was doing for us, right? By going over that minimization, minimizing the sum of the square of the residual, find the best fitted line, right? Here we are going to say that, okay, let's say there are different methods out there, and actually there are different methods out there. Let me name some of them. So for instance, there's one called generalized least square, and we have weighted least square, feasible generalized least square, maximum likelihood estimator, and etc. Right? There are many different techniques out there that are going to do the same. Take some numbers here and give you back the beta hats, but the optimization technique behind the scene is different. So here we're gonna make a big claim, and it is very important. The claim is that if assumption number 1 through 5 is valid, so if you can confirm that assumption number 1 through 5, basically 1 through 5 is valid, then OLS is blue. BLUE, best linear unbiased estimator. Okay, so in terms of, well, E stands for estimator. We already know that OLS is an estimator, like GLS, like MLE, like FGLS. So U stands for unbiasedness. We already know that if I have the first 4 assumptions, then the OLS is going to be unbiased. Right here, I'm just reading through the slide. If I have assumption 1 through 4, the OLS is unbiased. Then in terms of linearity, that's basically our assumption number 1, right? Assumption number 1 is that the model is linear in parameter, right? However, here is, on this slide, we want to discuss, we want to claim that actually there's a theory, we are not going to go over the proof, but basically we claim that if we add assumption number 5, OLS is not only the unbiased version, it's the best version. And best is defined as the estimator with the smallest variance. Remember, at the end of the day, we wanted to use the sample size. We wanted to get as close as possible to this unobserved line. And we said that if the variance of these things is smaller, it's a better news. It means that if you're getting closer and closer to that unobserved population regression function, and the variance is small, it means that if you do it with another sample, the numbers are pretty much the same or close to each other, right? So this is a big claim. This is a big advantage of OLS versus the other estimators out there. It's a very simple technique, but at the same time, it's very powerful. But it's only powerful if all these assumptions are valid. So if the assumptions are not valid, you cannot claim that OLS is blue. Okay, so that was the big picture. Now let's go over the bullet points one by one. However, under these assumptions, there are many other estimators out there. So these are the list of other estimators. By the way, we're going to cover GLS, weighted GLS, and FGLS in the class as well. We're not going to do a maximum likelihood estimator, but we're going to cover the rest of them. So the second bullet point says that, okay, all of these things under assumption 1 through 4 are already unbiased. Okay, which one of these unbiased estimator has the smallest variance? That's the best one for us, right? So the one among these things, the one with the smallest variance is the one that's going to be very, very powerful, because not only it's unbiased, it's hitting at the target, the variance is small, right? So in order to answer this question, we have to consider a family of linear estimator. Let's say I use the estimated version of all those beta. I just showed them with beta tilde, right? I'm going to say that, okay, the output of OLS is going to be, let me use another color. The output of OLS is going to be beta hat 0, beta hat 1, beta hat 2. The output of the other estimators, all of them, I'm going to show them with beta tilde j in general. It can be beta tilde 0, beta tilde 1, beta tilde 2, and etc. And we're going to claim that, we can rewrite these beta tilde as a linear function of our y variable. I don't want you to get lost in the technicalities, because the proof is a little more technical. We have to do, I think it's beyond the scope of this course, but just remember that all the estimators that we discussed here, GLS, weighted least square, and etc., and including the OLS, can be written like this. Can be written as a weighted average of your y variable. Okay. Then we're gonna go over this theorem. The theorem says that the variance of all those other estimators, it's guaranteed to be larger or equal than the variance of the OLS estimator. So this is OLS versus others. And in this textbook, in this course, we're going to stick to the OLS until the very last chapter of the class, which is chapter 8, when we have heteroscedasticity, right? So remember, under assumption 1 through 5, we call OLS blue, best linear unbiased estimator. And so this is the unbiased part, and this is the best part. The linear assumption number 1 estimator is basically estimator. Okay, this is true only if assumption 1 through 5 holds. However, again, as I said earlier, if there's heteroscedasticity, which is a violation of assumption number 5, right? So MLR 5 is violated. If in that case, there are better estimators out there with lower variance. And so one example is weighted least square. We're going to look at that in chapter 8. So we have to, for the first 7 chapters, we're going to rely on our assumptions. We're going to say that, okay, assumption 1 through 5 is valid, and we're not worried about heteroscedasticity. But in chapter 8, we're going to see that in real world, there's a good chance that lots of our models that we're going to do, we're going to consider, are suffering from heteroscedasticity. And if that's the case, OLS is not going to be the best estimator anymore. And for your final project, there's a good chance that you're going to work with a data set that it's suffering from heteroscedasticity. You're not going to use OLS. But don't worry about a final project yet. I'm going to walk you through the details of that final project after midterm 2, which is, I believe, it's the right time. All right, so let's sum it up. This is the end of chapter 3. So far, we have 5 assumptions that we already made. What I want you to take away is that with the first 4 assumptions, OLS is unbiased. If I add the 5th assumption, which is the homoscedasticity, OLS is blue, best linear unbiased estimator. All right. There is a slight section in the text at the end of the chapter 3 in textbook that talks about, makes some comments about the language of multiple regression model. Okay, basically this is something that you're going to practice it a lot for your final project. Basically the narration of your final project is going to be like this. But I just leave it here and maybe for your reference, and hope that you don't make that mistake. But again, if you make this mistake, it's not the end of the world, because these are very common mistakes that even myself or other friends of mine, when we are presenting at work, we say that we use a, I don't know, OLS model. OLS is not a model, it's an estimation technique. But let's read through them. These are some technicalities in terms of language of multiple regression model. OLS is an estimation method. It's an engine, it's a technique, it's a rule. It's not a model. Okay, so it is wrong to say that I estimated an OLS model. So if you hear someone says that, I use OLS model, it's a wrong statement. But again, these are just technicalities. Just be aware, as a graduate students from econometrics course, you should know what is wrong, right or wrong in terms of terminology. The proper way to introduce a discussion of the estimates is to say, again, this is basically what you do for your final project. You're going to say that I estimated the following equation, and whatever the equation you're using. So for instance, in this example, I just said, okay, the math in your grade 4 is a function of the size of the class in grade 4, the math you got in grade 3, maybe the income of the family, your mother education and father education, right? And you make some arguments like this. Again, think of it as your final project. You have to say, first, make sure that the assumptions 1 through 4 are valid. So assumption number 1, linear parameters, take. Assumption number 2, random sampling. We assume that the data is random sampling. Assumption number 3, we assume that the model is not suffering from perfect collinearity. Actually, this is obvious here, right? I don't see a perfect collinearity between class size 4, math 3, income, father education, mother education. If I had total parent education in this equation, that model was suffering from multicollinearity, because mother education plus father education is equal to parent education. So I had to drop one of them, either mother or father or parent, right? But here, this is perfectly fine. So assumption number 3 is also valid. Assumption number 4, we're going to say that, okay, we argue whether it's reasonable to maintain assumption number 4 in the model by focusing on the factors, so this is important, by focusing on the factors that might still be in the U. So you're going to make some arguments. And this is the art part of the econometrics. So this is not science. You have to make arguments, say that, it seems to me as a researcher, there's not many more variables out there left out that I'm not including in the model. So I think that math in the grade 4 is a function of these variables and nothing more. And if someone from the audience said that, did you control for that? And if you really hadn't controlled and you had data to control for that, you have to say, okay, yeah, you're right. I will go back and add that one to the model, so x6, and then rewrite, redo all the regression analysis and come back to you with the new numbers. Okay. But again, this is the art part. So you have to convince your audience that why you included some variable in the model, why you dropped some variable from the model, and the consequences. Because if you add an irrelevant variable, it will, something will happen to the unbiasedness and the variance. If you drop some relevant variable, the model is going to suffer from omitted variable bias, right? So the purpose of this chapter was to help you with correct specification of the model, neither under-specified nor over-specified, right? Then basically you say, okay, if these four assumptions are valid, then the model is unbiased. This is this bullet point. And then if the error terms has constant variance, this is basically assumption number 5, right? Homoscedasticity. Then my estimator, OLS, is going to be blue, best linear unbiased estimator. Okay, that's pretty much it. I guess, yeah, it only took us 25 minutes, maybe 24 minutes. So it was relatively a short and quick one. Make sure that when you come to the class, we're gonna spend 30-40 minutes on this couple of slides. I want to make sure that you understand by using Venn diagrams, you're completely, confident with derivation of these relationship between beta hat 1 and beta tilde 1. Okay, till then, I'll see you in next class.